This talk is about basic electronics for clinical neurophysiologists. The purpose of this talk is to explain some important concepts about filters. This talk will be conducted in a question and answer format. It will start from where we left off in part 1 of this series. The first question is the waves contributing to the sensory nerve action potential and to the compound muscle action potential have a similar frequency, range, and intensity. A true, B false. Using direct current filters at the low end and fast frequency filter of 3000 Hz at the other end of the spectrum, the frequency of the waves and proportion or intensity of each frequency contributing to the shape of the compound muscle action potential have been determined. They range from waves longer than 1000 milliseconds close to direct current to waves of about 1 millisecond, that is 1000 Hz. Most of them lasting longer than 6.6 milliseconds. On the other hand, the waves contributing to the sensory nerve action potential have a much wider range. They range from some lasting just 0.33 milliseconds or 300 Hz to some lasting more than 1000 milliseconds, that is close to direct current, with most of them falling between 6.6 milliseconds and 1.3 milliseconds. So the answer to this question is false. Brain electrical activity is limited to producing waves measuring from 2 seconds to 20 milliseconds. A true, B false. Full band EEG has demonstrated that the waves generated by the brain activity range in frequency from very slow, almost continuous, to very fast. The term infraslow rhythm refers to the brain-generated rhythms made of waves ranging from 10 seconds to 100 seconds. It is interesting to remember that the first EEG machine was engineered to capture direct or continuous current and not alternating current as the one we currently use. The term ultrafast rhythm refers to brain-generated rhythms made of waves ranging from 100 Hz and above. The upper limits of ultrafast wave generated by the brain activity has been reported to be 1000 Hz by some investigators and 3000 Hz by others. The relative intensity of these signals vary from wave to wave and to my knowledge has not been reported. So the answer to this question is false. Next question. What subcomponents of a wave contribute more to its amplitude? A, the slow wave subcomponent. B, the fast wave subcomponents. C, both, the same. In this frame, I am depicting the subcomponents of a wave adding to the ultimate wave. The ultimate wave is the one we see during electrodiagnostic testing and used for calculations. It is important to know that the slowest sine wave contributes the most to the amplitude of the ultimate wave. On the other hand, it is the fastest sine wave that contributes the most to the rise time of the ultimate wave and therefore to the onset latency. So the answer to this question is A. Next question. What subcomponents of a wave contribute more to the rise time of a sine wave? A, the slow subcomponent. B, the fast subcomponent. C, both of them the same. This is an easy answer if you were paying attention. The fastest wave contributes the most to the rise time and to the onset latency than any other wave. So the answer to this question is B. Next question. Which of the following factors contribute to the geometry of a wave? A, amplitude. B, frequency. C, phase difference. D, all of the above. The parameters that influence the geometry of the ultimate wave are amplitude, frequency or duration of each wave, and phase difference between the different subcomponents of the ultimate wave. So the answer to this question is D. Frequency filters influence A. Duration, B. Peak latency, C. Waveform, D. All of the above. Frequency filters influence onset latency, duration, peak latency, amplitude, waveform, and area. These parameters are mostly used in relation to the first negative wave in most peripheral nerve electrodiagnostic testing, whereas with central nervous system testing, they usually rely on other waves in addition to the first negative wave. So the answer to this question is all of the above. Next question. Which of the following factors contribute the least to filter selection? A. Frequency component of a wave. B. Choice of latency of interest. C. Need for baseline stability. D. Known amplitude of a wave. Filter selection is based on the frequency components of a wave, bandwidth of interest, baseline stability, and the need to eliminate artifact, especially 60 Hz artifacts. So the answer to this question is D. Next question. When calculating onset latency, the higher frequency filter setting should be higher than when calculating peak latency. A. True, B. False. In general, electrodiagnostic tests that are calculated based on onset latency require a higher frequency filter setting that is in the range of 10 kHz, whereas those whose calculations are based on peak latency are usually done using high frequency filters of 3000 Hz. High frequency filter setting for single fiber EMG is usually 10 kHz because its calculation is related to the rise time of the potential. High frequency filters for visual evoked potentials are set at 250 Hz because of tradition and the need to avoid high frequency artifacts. High frequency filters for EEG is set at 70 Hz also because of tradition and avoiding high frequency artifacts. So the answer to this question is A. True. Next question. Which of the following studies require the highest setting of the low frequency filter? A. EMG, B. Nerve conduction, C. Single fibers EMG, D. EEG. Base stabilization is a function of the low frequency filter. The higher the low frequency filter is set at, the more stable the baseline will become. EMG, nerve conduction, and evoked potentials, except for visual evoked potential, typically use a low frequency filter set at 20 Hz, primarily for baseline stabilization. The low frequency filter for EEG and visual evoked potential is usually set at 1 Hz because baseline stabilization is usually not a major problem, and the range of band we want to study demands it. It is not appropriate to set the low frequency filter to conduct an EEG or a visual evoked potential to 20 Hz. For polysomnogram, the low frequency filter is usually set at 0.5 Hz because of the importance of capturing slow frequencies. Some authors recommend using a low frequency filter set at 0.5 Hz also for neonates. The later recommendation was done due to the predominance of slow frequency waves during this period of life. In single fiber EMG, the low frequency filter has to be set at 500 Hz. This is because baseline stabilization is very important in order to interpret this modality of studies. So the answer to this question is C. Next question. If you encounter 60 Hz electrical artifacts during electrodiagnostic testing, just use the notch filter. A. True, B. False. Notch filters are used as a last resort to eliminate artifacts, especially 60 Hz. So the answer to this question is false. Which of the following methods can be used to memorize the effect of filters upon vulnerable waves? A. Arrow method. B. Column method. C. Visual method. D. All of the above. In the next few frames, I will introduce to you three figures. They are methods I have used to recall the effects of filter upon waves. I do not want you to spend too much time studying them at this junction, since I will address each of them separately after this question is answered. I have already introduced a similar figure to you a few minutes ago. What I did not tell you then, but I will tell you now, is that you are going to see this figure and the other two figures I will introduce shortly over and over again. I like to call the method of memorizing based on this figure the arrow method. In this frame, I have introduced a second figure. This figure represents the second method I used to memorize filter function. I refer to this method as the column method. And in this frame, I am introducing the last method I used to memorize filter function. I refer to this method as the visual method. All these methods have pros and cons, as you will see. So the answer to this question is D. Next question. Decreasing the low frequency filter modifies onset latency. A true, B false. To answer this question, I will use the help of the arrow method. Using this figure, I will present to you the effects of low frequency filters on the negative wave, because calculation based on this wave is the one most often considered during peripheral nervous system diagnostic testing. In this frame, I have introduced a white arrow to indicate the lowering of the low frequency filter. The lowering of the low frequency filter results in increasing the number of slow subcomponents or sine waves contributing to the ultimate wave. That is, the wave that we're now looking at has more slow waves contributing to it. The increase in the number of slow waves contributing to an ultimate wave do not have any effects on the onset latency of the wave. Will increase the duration of the negative wave, will increase, that is, delay peak latency, will increase the amplitude of the negative wave, will transform a triphasic wave into a diphasic wave, and will increase the area of the negative wave. So the answer to this question is false. Next question. Decreasing the low frequency filter in a wave with vulnerable components will modify it by all of the following except A. Decrease peak latency, B. Increase duration of the negative wave, C. Transform a triphasic wave to a diphasic wave, D. Increase amplitude. If we look at this frame, you are likely to be overwhelmed by so many little things in it, but I will go through this frame with you slowly as to mitigate this feeling. Let us start by looking at the low frequency filter. Now I have changed the color of the arrow just below the low frequency filter to aqua. I have done this to imply that the filter has been lowered from 5 Hz to 0.1 Hz. What we have done is to allow for more of the slower components of a wave to contribute to the geometry of the ultimate wave. So adding slow waves will increase amplitude, increase area, increase duration, increase peak latency, and it will not change the onset latency. Regarding the waveform transformation, adding slow waves to the ultimate wave will modify the shape of the wave by transforming a relative flat tracing to a tracing with more deviation from baseline, and will transform a triphasic wave into a biphasic wave. So the answer to this question is A. Next question. Decreasing a low frequency filter from 150 Hz to 1 Hz will alter motor nerve action potentials more than sensory nerve action potentials. In order to answer this question, we first have to understand the effect of decreasing the low frequency filter in a single wave. I will start with an intermediate frequency wave represented in bright red, to which I am adding a slower wave here represented in green. The product of this addition will change the geometry of the original wave, again represented here in bright red, whereas the original wave is now represented in faded red. From analyzing this diagram, it becomes easy to deduce and thus to remember what happens to all the parameters of a wave when the lower frequency filter is decreased and slow waves are added to the ultimate wave. Thus, decreasing the low frequency filter will have the following consequences. Amplitude will be increased, area will be increased, duration will be increased, peak latency, here indicated to be 5 seconds in the original wave, will be increased to 10 seconds in the resulting or ultimate wave. Onset latency, on the other hand, will not change. So, having considered the first part of this question, that is the effect of decreasing the low frequency filter, we must now consider the second part of this question, and that is the difference between the composition of motor nerve action potentials and sensory nerve action potentials. For this purpose, I am reintroducing this figure. As you know, most of the activity contributing to the compound muscle action potential falls between less than 1 Hz and 150 Hz, whereas most of the activity contributing to the sensory nerve action potential is between 150 and 750 Hz. So, if we use a high frequency filter of 3000 Hz and a low frequency filter of 150 Hz to record both motor and action nerve action potentials, as I have represented in this frame between the green lines. In this new frame, I have removed the frequencies between direct current and 150 Hz. I have represented this removal by restricting the bandwidth as you see here. So using these filters, only 30% of the waves that normally would contribute to the compound motor action potential will do so, whereas the ultimate wave generated by sensory nerve action potential will be constituted by 80% of its subcomponents. Were we to change the low frequency filter from 150 Hz to 10 Hz, 90% of the subcomponents usually contributing to the geometry of the compound muscle action potential will do so, representing a gain of about 60%. On the other hand, the gain on the sensory nerve action potential will only be from 80% of the total wave when using a low frequency filter of 150 Hz to 95% of the wave when using a low frequency filter set at 10. Hence, the change incurred by the compound motor potential is greater than the change incurred by the sensory nerve action potential with such filter change. So the answer to this question is true. Next question. Decreasing the low frequency filter transform a diphasic wave to a monophasic wave. True or false? This frame shows two tracings. All parameters are the same for all two tracing except the low frequency filter. Here, the low frequency filter is at 1 Hz, and as you can see, the highlighted area in this frame shows a diphasic wave. Now, if we look at what happens when the same segment of the tracing is viewed using a low frequency filter setting of 0.3 Hz, you can see that the positive segment of the wave is gone, thus turning the segment of the tracing from a biphasic to a monophasic wave. So the answer to this question is true. Next question. Decreasing the low frequency filter transforms a triphasic wave to a diphasic wave. A, true, B. False. As illustrated in this cartoon, a triphasic wave with corresponding vulnerable basic rhythms, when viewed with a low frequency filter of 1 Hz, will be transformed into a biphasic wave if the filter is changed to 0.3 Hz, and a biphasic wave captured using a low frequency filter of 0.3 Hz can be converted to a monophasic wave if the filter is changed to 0.1 Hz. So the answer to this question is true. Next question. Which of the following techniques can accentuate a suspected slow wave focus? A. Decreasing the low frequency filter. B. Reducing paper speed. C. Increasing gain. D. All of the above. If we are using a filter of 2 Hz and decrease the low frequency filter to 0.2 Hz, we are adding a slow basic rhythm to the geometry of the wave or to a given segment of the tracing. So decreasing the value of the low frequency filter, as we have previously stated, adds low frequency basic rhythm to the tracing, thus enhancing a slow activity. You can see in this EEG tracing an example of recording using a 5 Hz low frequency filter. Below is the same segment of the tracing now using a 1 Hz low frequency filter. As you can see, the slow waves which were not visible when using a 5 Hz low frequency filter are now visible when using a 1 Hz low frequency filter. So the answer to this question is A. Next question. Decreasing the low frequency filter increases the amplitude, area, duration, and peak latency of the vulnerable waves. A. True. B. False. I will use this figure to show the effects of lowering the low frequency filter. I hope that it will make it easy to remember. When we decrease the low frequency filter, in this case from 5 Hz to 0.1 Hz, all parameters affected will increase. I have represented the increase in those parameters in this frame by changing the color of the arrows from white to black, and a flat tracing will become a wavy one. So the answer to this question is true. Next question. Increasing the low frequency filter while looking at a low voltage record can lead to a pattern similar to hepatic encephalopathy. A. True. B. False. In this frame, I am depicting the 3 methods that you can use to remember the effects of filtering on waves. I have used this diagram before. When dealing with low frequency filters, an increase leads to a decrease in the amount of a slow basic rhythm being added to the geometry of the ultimate wave. Such an action does not alter the onset latency of the wave. Remember, changes in low frequency filter do not touch onset latency. Decreasing the low frequency filter will decrease the duration of the negative wave, will decrease the peak latency, will decrease the amplitude of the negative wave and the area of the negative wave. Increasing the low frequency filter will transform a biphasic wave into a triphasic wave. Triphasic waves are the hallmark of hepatic failure. So the answer to this question is A. Next question. Filtering can turn the polarity of a wave. A. True. B. False. In this tracing, we are using a low frequency filter of 1 Hz. Notice the T5 electrode and the highlighted area of the record. This highlighted area indicates a negative wave arising from T5. Now, if we go back to the low frequency filter and we change it to 5 Hz, we see a relatively small change occurring. But if we go back to the low frequency filter and change from 5 Hz to 7 Hz, you can see that the once negative wave at T5 has now turned into a positive wave at T5. So the answer to this question is true. Next question. Which attributes of a wave with vulnerable components will not be modified by increasing the low frequency filter? A. Peak latency. B. Duration of the negative wave. C. transformation of a biphasic wave to a triphasic wave, the onset latency. When we increase the low frequency filter, we are subtracting slow frequency waves. Let us use an example. If we use a 0.2 Hz frequency low frequency filter and then we increase the value of the low frequency filter to 2 Hz, we have actually removed from the wave a significant number of slow basic rhythms. The impact of removing all these subcomponents can be deduced by looking at the behavior of a single wave and using the visual method to do so. Let's say that we have a wave. The wave is represented here in bright red. That wave itself is a product of two different subwaves. The subwaves are here represented as a yellow wave and a green wave. And as we subtract from it the slowest of the two waves, as we have done well in this frame, the resulting wave will have certain characteristics. There will be no change in onset latency. The peak latency will decrease from, let's say, 10 milliseconds to 5 milliseconds. The duration will decrease, the amplitude will decrease, the area will also decrease. Increasing the low frequency filter while observing a monophasic vulnerable wave will demonstrate the expected negative wave changes, that is, decrease in amplitude, duration, area, and peak latency, but will also change the appearance of the wave by producing or increasing the duration and the amplitude of the positive wave following the first negative wave, thus transforming a monophasic wave into a biphasic wave and a biphasic wave into a triphasic wave. So the answer to this question is D. Next question. In a nerve conduction study, horizontalization of the baseline can be achieved by judicious increase in the low frequency filter. A true, B false. This is a representation of a nerve conduction study. The low frequency filter is set at 1 Hz and the high frequency filter is set at 10,000 Hz. As you can see, the slope of the study leading to the first negative wave has a steep incline. This steep incline makes measurement of the onset latency difficult. If confronted with this situation, what we need to do is to increase the low frequency filter from 1 to 100. The slope will, after we change it to the low frequency filter to 100, will change shape, and thus the onset latency will be easily measured. But if instead of increasing the low frequency filter to 100, we were to increase it 300 Hz, measuring the onset frequency will once again become difficult because of the shape acquired by the wave. So the answer to this question is true. Next question. Increasing the low frequency filter decreases the slow waves in a tracing and decreases the amplitude, area, duration, and peak latency of vulnerable waves. A true, B false. The effect of increasing the low frequency filter is to decrease the amount of a slow wave basic rhythm contributing to the ultimate wave. Thus, it will decrease all measurable parameters of a wave and change the characteristic of a tracing by turning monophasic waves into biphasic waves and biphasic wave into triphasic waves. Ultimately, excessive use of this filter will produce a flattening of the background activity. So the answer to this question is true. Next question. Increasing the high frequency filter adds thin waves. A true, B false. If you are using a high frequency filter of 15 Hz and then increase the high frequency filter to 130 Hz, the amount of fast basic rhythm contributing to a wave will increase. So an increase in high frequency filter will produce an increase in the number of fast basic rhythms contributing to a wave. The answer to this question is therefore true. Next question. Increasing the high frequency filter while looking at a wave with vulnerable components will decrease onset latency. True or false? To answer this question, I will start by introducing a slow wave in bright red. The vertical yellow line indicates the onset latency of the wave. In this cartoon, I will time the onset latency to 5 seconds. Now I will add a fast wave and draw the wave that will result from its addition in bright red, while fading the color of the original wave. Such an occurrence, that is the adding of a fast wave at the onset of a slow wave, will decrease the onset latency as depicted in this frame. In this cartoon, I have timed the onset latency after the addition of the fast wave to 3 seconds. So the answer to this question is A. Next question. Increasing the high frequency filter while looking at a wave with vulnerable components will decrease the duration of the negative wave. A true, B false. This frame shows a wave with a low frequency filter of 10 Hz and a high frequency filter set at 100 Hz. If the high frequency filter is raised to 500 Hz, the wave will undergo the changes depicted in this frame. The duration of the wave will be shortened. If now we use a high frequency filter of 2000 Hz, the configuration of the wave will be as you see it in this frame. The duration will be even shorter. And were we to use a filter of 10,000 Hz, the configuration of the wave could be as shown in the aqua color, and the duration would be even less. Hence, the answer to this question is true. Next question. Increasing the high frequency filter while looking at a wave with vulnerable components will delay peak latency. A true, B false. I will again use the visual method to explain the changes that occur to peak latency. You can see in this frame the representation of a slow wave. The vertical white line indicates the peak latency of the slow wave. Now I have introduced a fast or thinner wave. The incorporation of this faster basic rhythm wave to the original wave will produce characteristic changes. In this frame, I have faded the red line to indicate the original wave and introduce a bright red wave to exemplify the resulting wave. In this frame, I have introduced the peak latency of the resulting wave by placing a vertical line on the bright red line. The result will be that the peak latency will be decreased. So the answer to this question is
B. False.
Next question. Increasing the high frequency filter while looking at a wave with vulnerable components will increase the amplitude of the negative wave. A true, B false. I will again use the visual method to depict the changes in amplitude produced by increasing the high frequency filter. The incorporation of this faster subcomponent to the original wave, here represented now in faded red, will yield a wave with a characteristic depicted by the bright red wave. It is obvious that the effect of adding faster wave components to a wave will show an increase in amplitude. The arrow just introduced indicates the amplitude of the original wave. The second arrow, the amplitude of the resulting wave. So the answer to this question is true. Next question. Increasing the high frequency filter while looking at a wave with vulnerable components will transform a monophasic wave into a biphasic wave. A true, B false. I will again use the visual method to depict the effect of adding fast waves. Here I am representing an imaginary wave using a low frequency filter of 10 Hz and a high frequency filter of 100 Hz. This imaginary wave is vulnerable to the effects of the cited filters and to the ones I will introduce in the following frames. Here we are using a high frequency filter of 500 Hz, here one of 200,000 Hz, here one of 10,000 Hz. As you can see, the higher the high frequency filter is used, the thinner the negative wave becomes, and the more prominent the positive wave that follows the negative wave becomes. So the answer to this question is true. Next question. Increasing the high frequency filter while looking at a wave with vulnerable components will decrease the area of the negative wave. A true, B false. This frame demonstrates the area of the negative wave when using a low frequency filter of 10 Hz and a high frequency filter of 100 Hz. Now you can see the change in area produced by increasing the high frequency filter. Simply stated, the area of the negative wave increases with addition of fast basic rhythm to a wave. So the answer to this question is false. Next question. Increasing the high frequency filter on a vulnerable wave while looking at a tracing increases the amplitude and the area of the negative wave while decreasing the duration, onset latency, and peak latency of the negative wave. A true, B false. The effect of increasing the high frequency filter is to increase the amount of fast wave contributing to the ultimate wave, thus an increase in amplitude and area. Remember, adding waves, whether fast or slow, always increases the amplitude and the area. But adding fast wave has an unusual effect on the duration, peak, and onset latency of the negative wave. Adding fast waves decreases them. The effect of adding faster frequencies to a wave is as expected to increase the number of peaks, thus transforming a monophasic wave into a triphasic wave. So the answer to this question is true. Next question. Decreasing the high frequency filter while looking at a wave with vulnerable components will A. Subtract fast wave components, B. Increase the onset latency, C. Increase duration of the negative wave, D. All of the above. Decreasing the high frequency filter subtract fast frequency waves from the wave being studied. The effect of such a phenomenon will have on vulnerable wave consists of increasing onset latency, increasing the duration of the negative wave, increasing peak latency, but will decrease the amplitude of the negative wave as it will decrease the area of the negative wave and turn biphasic wave into monophasic waves. So the answer to this question is all of the above. Next question. Decreasing the high frequency filter while looking at waves with vulnerable component will A. Add fast components, B. Decrease the peak latency, C. Not affect the shape of a diphasic wave, D. Decrease the area of the negative wave. In this frame, I am representing a low frequency filter fixed at 10 Hz and a high frequency filter fixed at 10,000 Hz. You can see the configuration of the wave. In this frame, I have changed the high frequency filter to 2000 Hz. Here, I have changed it to 500 Hz, and here the high frequency filter is set at 100 Hz. Please take a few seconds to appreciate the changes in configuration that has taken place as the high frequency filter is being decreased. So the answer to this question is D. Next question. Decreasing the high frequency filter on a vulnerable wave while looking at the tracing decreases the amplitude and the area of the negative wave while increasing the duration, onset latency, and peak latency of the negative wave. A. True, B. False. The effects of decreasing the high frequency filter is to decrease the amount of fast rhythm contributing to the ultimate wave. Thus, as we have stated previously, the subtraction of any subcomponents from a negative wave, regardless of if the subcomponent is a fast or a slow subcomponent, decreases the amplitude and the area of the wave. The subtraction of fast wave increases the peak and onset latencies of the negative wave and has a rather unexpected consequence on the duration of the negative wave. It increases the duration of the negative wave and will modify a wave morphology. will decrease the phases of any rhythm and may turn triphasic waves into a smooth monophasic waves. So the answer to this question is true. Using a high frequency filter of 15 Hz will not attenuate an EEG spike. A true, B false. A spike is defined as a sharp wave lasting less than 70 milliseconds and more than 20 milliseconds. Were we to use a 15 Hz high frequency filter, a significant portion of the basic rhythm contributing to the spike will be attenuated. In this frame, I am introducing a spike and wave complex to demonstrate the effect of high frequency filter. Using the parameters shown above the wave, which include a high frequency filter setting of 70 Hz, the amplitude of the spike is 232 microvolts, keeping all parameters the same except for the high frequency filter, which has been changed to 15 Hz. The voltage has dropped to 188 microvolts. This represents a 20% drop in amplitude. So the answer to this question is false. Next question. A high frequency filter of 70 Hz will minimally decrease the amplitude of a spike. A true, B false. This frame represents the frequency of a spike. Were we to use a filter of 70 Hz, there would be hardly any attenuation of all the rhythm contributing to the spike. So the answer to this question is true. Next question. Decreasing the high frequency filter may turn a spike into an innocuous looking wave. A true, B false. Please note the shaded ovoid area. This area contains a spike. Also note that the high frequency filter has been set at 70 Hz. In this frame, the high frequency filter was decreased to 5 Hz. You can see the changes that have occurred in the shaded area. The spike is no longer present. So the answer to this question is true. Which of the following waves will be attenuated by a bigger factor when using a 70 Hz high frequency filter? A 70 millisecond wave, B an alpha wave, C a beta wave, D a 10 millisecond wave. Delta waves have a duration between less than 1 second and 250 milliseconds. A high frequency filter of 70 will not touch them. Theta waves have a duration between 250 and 125 milliseconds. A high frequency filter of 70 Hz will not touch them either. Alpha waves have a duration between 125 and 77 milliseconds. A high frequency filter of 70 Hz will not touch them either. Beta waves have a duration between 77 milliseconds and 33 milliseconds. A high frequency filter of 70 will not touch them either. Spikes are defined by their sharp activity and by having a duration between 70 and 20 milliseconds. A high frequency filter of 70 Hz will attenuate the fastest component of a spike, that is those lasting close to 20 milliseconds, by about 20%. But again, this will be dependent on the role of the filter being used. A 10 millisecond wave will be attenuated by about 50%. Again, this will depend on the role of the filter. So the answer to this question is D. Next question. Changing a high frequency filter from 70 Hz to 15 Hz may change a spike into a sharp wave. A true, B false. With a high frequency filter at 70 Hz, the duration of the selected wave is 63 milliseconds. This duration qualifies the wave as a spike. With a high frequency filter set at 15 Hz, the duration of the selected wave is 78 milliseconds. This duration qualifies the wave as a sharp wave. So the answer to this question is true. Next question. Increasing the low frequency filter from 0.1 Hz to 5 Hz will decrease the amplitude of the negative spike and the slow wave. A true, B false. With a low frequency filter set at 0.1 Hz, the amplitude of the selected wave is 227 microvolts. With a low frequency filter set at 5 Hz and no other changes, the amplitude of the selected wave is 187 microvolts. The changes to the spikes are also easily perceptible. So the answer to this question is true. Thank you.